Welcome. Let's solve Leetcode 1765, map of highest to peak. All right, so let's make this bigger so we can read it. So we're given an integer matrix is water of size m by n that represents a map of land and water cells. So if is water, the cell is 0, if the value of the cell is 0, then it's a land cell. If is water value is 1, then it's a water cell. You must assign each cell a height in a way that follows these rules. The height of each cell must be non-negative. If the cell is a water cell, its height must be 0. Any two adjacent cells must have an absolute height difference of at most 1. A cell is adjacent to another cell if the former is directly north, east, south, west, or west of the latter. Find an assignment of heights such that the maximum height in matrix is maximized. Return an integer matrix height of size m by n where the value of each cell is its height. If there are multiple solutions, return any of them. Okay, for example 1. So this diagram, to be clear, is not the input, it's the output they expect. So the input is this is water array or list, and notice this value is 1, which corresponds to the upper right corner, which is the water cell, and it's 0 in the returned value. And the neighbors of this cell are 1, and then we can increment, we can go up so that this bottom left corner has a height of 2. Same thing over here for example 2. We're given an is water array here, and notice there's 2 1 values, and notice how the return grid has 2 water cells, and this would be the expected something similar to this return value. Okay, so I think that's enough for us to get started. I think the problem is somewhat straightforward. So what we're going to be using is breadth first search, and we'll be starting with we'll perform some sort of pre-computation that will figure out where to start with, and we'll start with the water cells and then perform breadth first search, adding 1 to the height of each neighboring cell. Okay, so let's start off with a small example here. So suppose our input looks something like this. So remember, I know this is one-dimensional, but my approach still stands. It's easily applicable to 2 dimensions. So they tell us that whenever we see a 1, that's a water cell. So our output would look something like this. This should be a 0 here. And what we'll be doing is, in order to save on space, in order to reduce the time complexity, we're actually going to reuse this is water grid. So when we perform our pre-computation, we're going to say what we'll be doing is we'll convert 1 to 0 and 0 to -1. So -1 will mean we have not explored it yet. So we'll be looking through our input here, and we'll convert this to we'll be following this conversion table here. So having described that, let's do it. So we do something like this here. So we would convert, well, let's change all these zeros to -1. And then we'd change this 1 to 0. This is what we'd be starting off with. This would be our grid. And then we would have a double-ended queue here that stores our water cells, and then corresponding neighbor land cells, etc. That's what we'll be doing. So, and then at the end, we'll have something like, so for example, we would start with a 0 here. And then remember, these are all, well, let's copy this down here. So on our first iteration, we'd have something like this. So we'd have 0, then we'd say, okay, let's pop this cell up and say, okay, our neighbors, let's change this to 1 and this to 1. And then these guys, this -1 would be added to the queue, so we'll call this length. So this would be added here. And then this would be popped off because we have no more water cells. And then now we have these two guys. And then remember, the neighbors of this cell is actually the 0 here, which is water, and this one. But whenever we see -1, we know that's not explored yet. So we would only, focus on this cell, not this one, because we know we have already explored this. So we would make this 2 and then add this to the queue. And we'll notice I'm storing the height here. So that's how I know to increment the next one. Okay, and that's about it. And for those who are not familiar with why I chose a double-ended queue, so double-ended queue, it provides O1 sorry, time complexity when removing, or maybe just removing items to either end of the queue. That's why it's called a double-ended queue. So typically, like a list, for example, a list is optimized to append and pop elements from the back. But because we're using breadth first search, we'd like to explore the cells on the left first. So we'll pop elements from the left and add child cells to the right. So the cells on the left will take priority over cells on the right. Okay, so let's begin. So whenever we're working with the grid, it's always helpful to get the dimensions of the grid. Okay, so now we have the dimensions. And now let's instantiate our double-ended queue, commonly known as a deck. Sorry, let's do this here. Okay, and this, just so you know, this comes from I think the collections library. So from collections import. So our Leetcode makes it convenient. They already import common libraries for us, so we don't need to do that. But if you were doing this locally, you would need it on your machine or something like that. You would need to import it manually. Okay, so now let's loop through our is water and find where the water cells are located. So remember, if it's a 1 here, that means we know we have water. So we can say, okay, we're going to change you to water. And then we're going to add you to our queue. We're going to say queue.append RC. Otherwise, if it's not water, it's land. So let's say, okay, we're just going to change you to land or unexplored. So we know we haven't visited you yet. Okay, let's print this out so we just get a good look of what we're working with so far. And let's just return the array so we don't get an error, or the grid. Okay, so notice here, this was our input, 0, 1, 0, 1, 0, 1. And now what we started with is this here. We have a 0 here in the right-hand corner, which is equal to what they're expecting, and we have the other cells, the land cells, as -1 because we haven't visited them yet. Okay, cool. Now let's begin our breadth first search. So we'll say while q, and I'm going to say okay, rc equals q dot. Remember, we want to pop from the left here. Those are the cells that take priority. So I'm going to do something here. I'm going to manually check left, right, up, and down. So I could use a for loop, but I'll explain to you why I do not use a for loop here. So r plus 1 is less than 0. So here I'm going to add the new cell to the back of the double-ended queue. So notice here we're popping the cells from the left. Those are the ones that have priority. We want to explore those first, and then we're adding the other cells. So imagine, like in this case, we have 2 water cells. So we need to explore these water cells before we explore the 1 cells or anything else really. And then once we find the 1 cells, we've explored the 1 cells, then we can move on to the 2s. So that's why we're doing this using the double-ended queue. Okay, and now we need to do something similar for when we subtract 1 from the row. So whenever we see r plus 1, let's change that to r minus 1. And we want this to be greater than 0. Greater than or equal to 0. Okay. And then now let's do maybe something similar for the column. So we'll say if column plus 1 is less than column, okay, convert this back, leave that alone, and then we change this over here. Okay, so we want this. Looks good so far. And then finally, we want to do the same thing for when we subtract 1 from the column. And this should be greater than or equal to 0. Greater than or equal to 0. And I think we return there. That's fine. So let's submit it, or let's test it. Let's submit it. Okay, looks pretty good. Top 99%. Now, the question becomes, well, why didn't I use the loop here? Well, let me show you why. What I've noticed is there are certain times when you use a loop is a mechanism that has slightly more overhead than an if-else clause, or in this case, just an if clause. So if I convert this to a for loop, I'll demonstrate to you that it's slower. And so what I've noticed is like we on Leetcode like our code to be faster than everybody else's. So if you want to do the structures or better algorithms, and one is removing unnecessary overhead. And so let me show you why. We don't necessarily need a for loop, but let's see what happens when we do use a for loop. So this goes here. Okay, and then we say rc equals rr plus dr. Then we want to check if the bounds, if this row and column are in the proper bounds. If it is, then we can do this here. So we could say this new row and new column are equal to the current cell plus 1, and then we add it to the queue, and then that's it. Let's test it locally. Oh, my apologies. None of this, sorry. Oh, sorry. Okay, looks good, and let's submit it. And we should see that it's significantly slower. I must admit, though, the code is far more succinct. Again, but notice how much slower it is than our previous version. So it's up to you. If you want to, have, this looks pretty readable and it's almost pretty. So it's up to you what you're aiming for. So I wanted to point out two different approaches, and it's up for you to decide which one you like best. Okay, if you found this video helpful or educational, please consider liking or subscribing. Other than that, have a wonderful day. Take care of yourself. Cheers.